I'm Dr. Valentin Voroshilov. After grading this lab for 7 laboratory sections, I decided to make this video. Understanding this material is crucial for understanding all Newtonian mechanics. But some students demonstrated some serious misconceptions that should be fixed as soon as possible. My conclusion was made based on my long and successful teaching experience. My student feedback may seem controversial, which is absolutely natural. But so far, I've always had students who really appreciated my teaching style because my style is based on the fact that to succeed in physics, one does not have to excel in algebra or geometry. A simple self-check can help to fix any math-related issues. The most important abilities are imagination and reading and writing. I myself have no formal education in English language. I learned it from books, TV shows. That is why I always try to express myself as clear as possible, and students should also train themselves in making clear speech. In theory, everyone can get an A, but for some students it may be easier than for others, which is also very natural. Einstein said that education is not just learning of facts, but the training of mind to think. Well, I know how to train the mind to think, and I've been training students to think for a long time, but the first part of this statement needs a correction. This is how it should sound. Education is not just the learning of facts. Learning facts is a very important part of education. In fact, learning physics is 95% just learning facts, laws, definitions. That's what makes physics simple. Physics is the second, after math, simplest subject to learn. It has a very clear, basic logic based on well-established facts. And the very first fact is based on a very simple observation. We, humans, are not blobs. We have many different organs responsible for many different functions. Legs are responsible for walking, teeth for chewing. The organ responsible for thinking is our brain. Hence, training a mind to think is nothing but training the brain to act. We, humans, are the only animals that use a brain for a specific function, making a decision. Other animals don't make any decisions. Their brain reacts only on signals coming from the outside of their brain. A human brain can generate a reaction to signals coming from the inside of that brain. The process of generating that reaction in the form of a decision involves, absorbing information, transforming information, creating new information, and transmitting information. That is why training a mind to think is essentially training a brain to process information. There are more types of information a brain can process, the more effectively a brain functions. The more types of learning activities required from student, the more advanced his or her learning process is. That is why just watching lectures is a very poor way to learn. But even that activity needs to be structured in a certain way. And that is why reading lab instructions is a very effective way to learn. Of course, if instructions are good, Vivid Interactives offers a set of nice videos, but making videos is no brainer. I've made more than 100 of those. However, their instructions are essentially useless. That's why for each lab I have to write something. I would say the great thing about physics is that physics has instructions for everything, starting from a general instruction on how to approach any problem. And the number one requirement for every lab, well, including this one, is to read the instructions in full before starting any lab. You work today now? When instructions say, no, you don't work today. The system you study is composed of two connected objects. But a student tells me the system is composed of 7. That student either didn't read the instructions or did not process the information in full. That student either didn't pay attention to important parts of the strategy for doing lab, or well, maybe didn't care much. Well, learning how to read instructions is a standalone learning practice. It requires a special effort. So, let's turn our attention to the lab. First, what we read is, you have to apply Newton's second law to each object. Well, the strategy for every problem eventually requires us to draw a picture. Every problem in physics has to be starting from a picture. Well, for that we have to look at the video, what's happening there. And, well, again, we have to follow the instructions, set the mass of the whole system to 600 grams, and load one video after another. Now we have to use some tools. We need to know how to use them. Well, just click. We can't adjust the location of the cart because the cart must begin the motion from the rest. So we have to adjust the location of the ruler to measure distance as accurate as possible. Now, instructions say you have to set the timer to the instant when the ribbon is being just cut. Oh. Go back, go back, go back, go back, go back. Do it manually. Here. This is the first instant, which should be set to 0. Set to 0. Now, we watch how it moves until it travels a specific distance. Let's say 30 centimeters. 30 centimeters is fine. We have to stop it. And, oops, wrong direction. 30. So now we have everything we need, and we have to repeat it again and again and again. But again, we have to start from a picture. So we just have to copy what we saw. Two objects are involved in this situation. Then instructions say, apply the Newton's second law for each object. Well, we can't apply what we don't know, so we have to know the law. And many students, when I asked, told me the wrong statement. They say F equals MA. Okay. And there's a big issue with that. Many students who said F equals MA made a mistake because there's one crucial word that was missing: net or total. What does it mean? Well, there is a definition for that. And when you watch a lecture, when your lecturer says a definition or write an equation, says a law, you have to pause it, take your notes, and start preparing your own equation sheet at the back of your notes. So you would be flipping through the pages. You would know exactly where to find all important fundamental information. So what does net mean? Net means the sum of all forces. What does sum mean? Well, addition, force 1 plus force 2 plus etc., etc. And even this expression is still wrong, because the full statement says the vectorial sum of all forces acting on an object is equal to the product of the mass of that object and acceleration of that object. So first of all, there is a big difference between a force and a mass, or acceleration and a mass. A mass is a scalar, acceleration and force are vectors. If you forget that difference, you make a mistake. Now, what does vectorial sum mean? Well, you have to know the rule for adding vectors. Vector A plus vector B will give you a resultant. A plus B, but we don't use usually a triangle when we calculating the net force. To calculate net force, most commonly we use a reference frame and we use components. So we have to introduce x and y axes, and now of course we have to draw all the forces. So we have the weight of a cart. We have normal force and the force of tension. Now those are vectors, and I have to show that I know that. Technically, they could have been the force of friction, but we have no information whatsoever about friction. So even if we wanted to account for that, we can't. That means we have to just neglect it, assume it's negligible. What else do we need to know? Well, we need to know a definition of force that has a name weight. The weight, by definition, is equal to the mass times g. Now we need to know the definition of g. G, by the definition, in all good textbooks from all good lecturers, is equal to the magnitude of a free fall acceleration. Free fall acceleration, which is 9.8 about meters per second squared. Okay. If we're calculating the weight of a cart, we should show, okay, cart. Of course, now we can write the Newton's second law using this specific set of forces. Force of tension plus normal force plus the weight of the cart equals the mass of what? Of the cart times acceleration of what? Of the cart. If you write an equation for the cart, everything in that equation has to be related to the cart. Well, now we can start using components. The transition from vectors to components is very simple, mechanical. You don't have to even think about it. You just stop drawing little arrows. You drop arrows, but you start drawing, well, writing subscript relative to x axis, relative to x axis. Do I have to do it here? No, that's not a vector, but acceleration is a vector. Same action relative to y axis, relative to y axis. Same mass relative to y axis. No thinking is involved at all. Now we have to think a little bit, because some components equal to 0. We talked about it in the lab number 2. If you have a vector that is perpendicular to axis, the component of that vector on that axis is 0. For example, the normal force doesn't have a horizontal component because it's perpendicular to x-axis. Same, the weight. Or else, force of tension does not have vertical component. What is missing? Well, we know because we see it, that when it released, the current starts traveling to the left, but it also starts traveling faster and faster. So the magnitude of velocity, or we call it speed, increases. We call it speeding up. And there's a rule: when object is speeding up, acceleration points in the same direction with velocity. So the acceleration also points to the left. That makes it horizontal. This symbol represents a vectorial nature of acceleration. This arrow represents the direction of acceleration. Every time when we draw a symbol, we need to know the exact meaning of that symbol. So the vertical component of acceleration will be equal to 0. See how many zeros? The more the better. Well, what else do we need to know? Components that are not zeros. For example, normal force has a vertical component, clearly. And there is a rule: if vector points in the direction of axis, the component is positive or positive, and is equal to the magnitude of that vector. So we just write magnitude. We don't write those vertical bars, but we know this symbol now represents the magnitude of the normal force. The weight, on the other hand, has a negative component, so I would write -1 times the magnitude of the weight, or just this. Horizontal components. Tension points to the left, opposite to x-axis. So tension relative to x-axis has a negative component. And we write it like this. And this symbol now represents the magnitude of the force of tension. Acceleration relative to x-axis has a negative component. We write it like this. And this symbol now represents the magnitude of the acceleration of the cart, technically. But now we can say that because the string connecting the objects is ideal, so we can't stretch it. It doesn't change its length. These objects travel same distance and same time, so they will have the same speed, the same acceleration. I don't have to use this subscript. Magnitude of the acceleration will be the same for both objects. All right, finally, all this stuff gets plugged in the equations. So what I get from here? So poorly designed software. I can't even use the presentation mode because it will work even worse, despite the fact that I've got i7 Intel processor here at 16 gigabytes of memory. Just very poorly designed hardware and software. for the remote teaching, there is no good hardware, there is no good software. No one makes it. Now, so what do we get from the y component? Very simple expression, lots of zeros. Basically, the result is obvious. The normal force must have the same component as the weight of the cart. In that way, they cancel each other out. Otherwise, the cart would be speeding up or slowing down in the vertical direction. And this is the most important equation for us. Plugging in everything gives us that the magnitude of tension will be equal to the mass of the cart times acceleration of the cart, which, as we said, will be the same for the cart and for the weight. This is the most important equation so far derived from the application of the Newton's second law to only one object, to the cart. Now we need to keep our analysis. So we've got a second object to consider, and it has two forces acting on it: the weight, which will be equal to the mass of that hanging mass times g, and tension. Technically, that's a different tension. It has a different direction. But again, because the string is ideal, massless, the tension inside will have the same magnitude everywhere. So we have to use a different symbol for that. And now we have to use only one axis. So in the video, we can see it is moving down, so velocity points down, and it travels faster and faster, speeding up. So acceleration will be parallel to velocity. And technically, we have to start from the general expression for the Newton's second law. But if we apply it to the vertical axis, tension has a positive component, weight has a negative component, and mass is just a number, but acceleration also has a negative component. And the magnitude of the acceleration is equal to the magnitude of acceleration of the cart. So this is the second equation we can use. And well, now we've got two equations. Of course, we also know that the weight of the hanging mass will be equal to the product of the hanging mass and g. Well, what do we do now? Read the instructions. And as I said, Pivot provides very, very poor instructions. For example, it forces you to do measurements and fill in the table and do the graphing before it tells you what graph do you have to plot. You have to go all the way back to question 4, and it says, make a graph of A versus WH. That means you have to make a graph for acceleration as a function of the weight of the hanging mass. And if you do make a different graph, you're losing points because you didn't read the instructions. This is supposed to be the graph. That means our table must have these two columns. So, question, do you measure in this lab acceleration and weight directly? Of course not, you don't. So you have to prepare your table. Not yet. I made a mistake, which is fine. Everybody makes mistakes. So, this is what I want to do. I need acceleration. Well, I can't measure it directly. So now I have to go back in time and figure out, how can I relate acceleration with measurable values? What do I measure? Distance, time. All right. So, what kind of a motion is happening? You have to answer that question. It's motion with a constant acceleration. How do I know? Well, technically I don't yet, because I didn't finish my derivation. Why? Because my graph has to relate these variables only, and I don't have an equation that relates these variables. I have to get rid of tension, which is an easy task. So I can just replace tension with this. That gives me mass of a car times acceleration minus the weight of the hanging mass will be equal to this product, and I move this over here, that over there, combine together, do some trivial algebra. Microsoft and Zoom together hate us, or maybe they're just incapable of writing good software that would work together. Times acceleration will be equal to amount of work. By some reason, sometimes it just stops communicating with the pen. Probably checking online if my office software is registered, wants to send some extra information about what I'm doing. Руки бы всем пообрывать. That was a joke. Okay, so now we can introduce a new definition. And we get a very simple equation that will relate these three variables: the mass of the weight of the hanging mass, the mass of the whole system, which is the sum of the masses, and acceleration. And I know that in this case, this parameter is constant. So I finally have an equation which will allow me to plot the graph. And since I know algebra, I know that this is a linear equation that has the form of y equals m times x, even no y-intercept. And in this equation, well, the slope of this graph has to be related to one of these parameters. All right, so I've got an equation. I know my goal now. So I have to start measuring time, distance, and then I have to write an equation that would relate these. Okay, so I have to go back to my notes, search for the equations with the motion with constant acceleration, because that's what it is. For each individual video, mass of a system is fixed, the weight of the hanging mass is fixed, so A is fixed, has a fixed value, constant. And the motion with constant acceleration, that tells me that I can use the motion equation. And in this equation, I just basically set this to 0, this to 0, and solve it for the acceleration. Well, x or d, distance times 2 divided by time squared. That's supposed to be my equation. The equation for the weight comes from measuring mass. So now we know what to do. Yeah, only now we know what to do. Distance, well, I'm going to use, let's say, meters. Variable d, time, seconds, oops, time, seconds, time, acceleration. Well, that's going to be meters per second, letter A. In my equation, so g times 2, I can use only the pad provided by the pivot divided by, well, just in case, because I'm not sure, do I need parentheses or not? When I'm not sure, I always use it. And you can write time times time, or you can write time squared, close parentheses, submit. So now, I don't know, distance 0.3, distance 0.3, oops, distance 0.3. Actually, you could just enter 0.3 in the equation for the acceleration, would work. Time, when the weight is 20, time, let's say, I'm just making up numbers, let's say 1 second, and then it travels faster because weight touch more heavier, weight, so 0.8, and with acceleration, right? So what else do we need? Masses. Oh, sorry. Again, I'm ahead of myself. First I need to add one more column. That's going to be mass, or the hanging mass in kilograms. Technically, when you fill in the table, you could use any unit, but then you would have to do calculations, and some students use the mixed units. That is a mistake. In order to lower the risk to make a mistake, just use international system of units in the first place. Well, that's going to be mass, and now we need one more column, and now we need to do weight. Weight will be now in newtons. Unbelievable. One letter is sufficient to describe. So 9.8. Submit, and let's say I get, I don't know, again, two masses. Now you go to a graph, and you know this must be acceleration. If it's anything else, you're losing points. This must be the weight. If it's anything else, you're losing points. And now you have to do a fit, and you know what fit you need to use, because the equation is linear. So you have to use the linear fit. Actually, proportional is the best one. Well, I don't know what it's doing. Sometimes the pivot actually has issues. When I have only 2 points, it should go to, eventually it goes to 0, because this is not 0 and this is not 0, right? Well, anyway, this is my slope. And you write everything now. Take a picture of your work or type it in, do this, do that. Question 4 is tricky. Some of you lost points because you didn't write anything. This is an active field, so it has to be actively used. What should you write? I don't know, anything. But it can't be left empty. And the last question about the slope, it tells you actually the slope of acceleration as dependent variable versus weight as independent variable has to be related to mass. It tells you. So, not sure why, but probably because you didn't pay attention. You tried to do some strange things. This is the graph. The fitting procedure gives you the value of the slope. I don't know, my slope was at 0.26, I think. Doesn't really matter, absolutely. Doesn't really matter. What matters is the equation I used looked like this. And clearly it's linear. So this is the dependent variable, which is an independent, this one. This is acting like y, this is acting like x. And what is between equals and x, that's the slope. What is between? Well, I don't see it. So I need to rewrite this equation in a form that I would have something in between. Well, if I just move w to the right, yeah, what's left is this. You can't leave an empty space in a fraction. It has to be something. Well, you know what it has to be. There's an invisible one as a factor, and when you move w away, that one becomes visible and remains there. So this is your slope. So this capital A, sorry. Capital A has to be equal to 1 over the mass of a system. Or the mass of a system will be equal to 1 over the capital A. In my fictional example, I think that was this number, which again does not matter. Yeah, 246 does not matter at all. What matters? Strategy, steps. Done with part 1. Moving on to part 2. The good thing about part 2, it doesn't require any new theory, because you're watching practically the same videos, same objects involved in the same manner, and the difference is only what is a new independent variable. You still have to plot the graph for the acceleration as a function of something. A function of what? Well, read instructions. The equation that relates acceleration, the weight of the hanging mass and the mass of a system is the same. But now what you change is the mass of a system. So your W, that parameter, will be fixed for all your videos, and it's going to be 0.08 times about 0.8 newtons, which is an approximation, but technically this is your equation now. So naturally you want to write the mass of a system as your independent variable. But again, algebra tells us this is y, this is x, y equals 0.8 over x. That's not a straight line. This is a hyperbola. This is not a linear function. This is not a linear graph. That is why you've been forced to do a specific procedure that is called linearization. So again, table. distance, time, acceleration. This part is not different. The mass of a system, but what you change from 400 and 600, etc., right? This is what the manual calls X. Of course, the letter doesn't matter. You could have used any letter. What matters is the meaning of it. This letter has to be set in such a way that the new graph for the acceleration as a function of this variable will become linear. This is your goal. Now, how do you get from this equation to this equation? The linear equation is slope times x. You have to read the instructions. They clearly tell you define, and then in parentheses, create, invent. So, this is an invention, a creation. This variable x is a result of an act of a creation, and only God does everything right from the first trial. So, when you need to create something, you make mistake, and then maybe again, and then maybe again. So it's natural. So you have to try and check. And well, in general, the list of possibilities is very long. So you have distance, time, acceleration, the mass number 1, the mass number 2, the mass number 3, G, tension, force, where else? Normal force, where else? Did I forget anything? I don't know. I guess that's it. But first of all, the instruction tells you that you need to invent the parameter in terms of mass. So this has to be the function of mass. Although you could use a logic, for example, let's try x equals time. Would it work? No, because you cannot use this setting, this definition in that equation. There is no time there. Let's try x equals a, or a times something, whatever. In that case, you will plot an acceleration as a function of itself. So, or distance, not a part of this equation. As well as other forces. Weight itself. Yeah. Well, weight is constant. So, trying a constant to represent a changing variable will not help. Come on. So, no, which is fine. Trial and error is the most advanced scientific method. Let's try x equals mass of a system. Well, how do we check it? Well, we solve it in terms of mass. I have to use the same letter. And now I can plug it in this equation and get the equation in terms of x. Look at it and make a decision. Is it linear or not? Oh no, this is not linear. So try again. Well, technically, mathematics has many functions, square root, power, something else. But again, if we look at the equation, if we separate the variables, we get the hint immediately. This is the dependent variable, this is constant. So this is probably a good candidate for checking. All right. A, oh, come on. Ax. This is my original equation. This is my assumption, hypothesis, or guess. So I can solve it for the mass of a system. So I could plug it back in my original equation, and that gives me this. Of course, you cannot leave it like that with two fraction bars, because it doesn't show you the nature of the equation. So you do some trivial algebra. Simplify always equation as much as possible. Is this a linear equation? You should ask yourself. Yes. Did you achieve your goal? Yes. That means this is the linearization parameter. Now you know that that last column, mass, x, should have a function of mass in this form. Plus now you know the slope, which is given by that capital A parameter, has to be equal to the weight of that hanging mass, which is about 0.8 newtons. So if you get 0.79, 0.86 or something like that, perfect. If you got 10 or, I don't know, 0.4, you made a mistake. Maybe your data is inaccurate, maybe you did algebra wrong, maybe something else. This is how it's supposed to work. So, well, if you have any questions, please send me an email. Bye. Thank you for watching.